Well, hopefully that's going to work. I didn't hear the little recording to the cloud thing now, so hopefully that will help. So, okay. So hopefully you all can hear me with my microphone. Let me just type in the chat. Are you able to hear me? And I'm just typing in the chat. It looks
Yes,
like
Professor.
oh, great. Okay. Fantastic. It just didn't look like I had any audio output. So, okay, fantastic. Let me also do this. I think we will be good. And let me also do this. Hang on 1 second. Let me just zoom it. Okay, fantastic. All right, now I think it was just that one last little hurdle I didn't achieve. So let's do this. Let me just show you really quickly for the cloud photo discussion, which by the way is chapter 7. It's totally part of assignment 6. Okay, like how do clouds form? Okay, so here is the deal, and let's just take a peek right here. All right, so this is your helpful. So, okay, basically, here's what it's all saying. So let me go to the next page right here. Let's see who's posted something yet. Okay, not yet. It's okay because it's like, the next discussion, and it's totally fine. So when you're ready to participate, let me just show you how you would post an image or a picture. I should have brought my own computer here, but let me do this really quickly. Let me do this. Give me one quick moment here with the screen share. Yeah, let me do this. How about this? Okay, lenticular clouds. Okay. These are cool. These clouds actually look like, there we go, Met Office. Okay. Actually, let me go to images right here. If you use, now you can use an image from the internet. Okay, let me share this with you on Zoom again, because I know you're like, Professor, we're just seeing a black screen. Hello. So these clouds are sometimes referred to, how to say colloquially, as UFO clouds, because they look like flying saucers. And I'm really not kidding about this. When people see lenticular clouds in our area, and they do form in our area because of our unique topography. We have mountains, right? I don't have to tell you that. You already know we have mountains. And so, and absolutely no fooling, people will contact their local police department or sheriff's department, like, I think we're being invaded, aliens from outer space. And it's like, well, no, ma'am, no, sir. Those are actually lenticular clouds. We're not, I swear, we're not being invaded from outer space. But these are relatively rare clouds that form, and you can see a little image right here, sometimes on the leeward side of mountains. So because we have mountains, and sometimes we have the correct atmospheric conditions, the wind direction is in the right place, we have enough mid altitude moisture available to create these clouds that are called lenticular clouds. So let me just show you really quickly, like maybe, let's see. Oh yeah, Scientific American. What the heck? This is pretty cool. This is actually a volcano that's erupting right here. I'm like, oh, that is so cool. So let me do this, and then I'll take a question here in a moment. So let me see. Let me do this. Let me see if I can pull this image to the desktop. Okay. Now, and then I will take your question. Okay. So, so Diego, so I typically have student hours from 10:30 a.m. to 11 a.m. Via Zoom and in person on Monday through Thursday. So I guess what I'm saying is, if you can join me between 10:30 to 11, Absolutely. And you're still welcome to stay, Diego, and play with us today. So absolutely. And by the way, this same discussion, I think you all have this in your lab class, if I'm not mistaken. So check this out really quickly. All right. So let me show you how to copy and paste and embed. So, hey students, check out this cool lenticular cloud image. And then let me see, where did I get it? Okay, I have to find out where I got it here. Okay, let me see if I can move this down. There we go. From Scientific American. Okay. Now, obviously, you'd want to give it like, March 19, 2024, blah, blah, blah. But okay, so Scientific American 2024. Okay. Now, to embed an image, here's what you all are going to do. So check this out right here. So we're just going to do this. We're going to do this. Okay. We're going to circle this right here. See this little thing right here that looks like a kind of a little picture icon. It's got the little caret, as they call this, pointing down. Okay. So let me show you right here. Check it out. You're going to love it. Okay. We're just going to upload an image. So just click on upload image. I am going to find it on my desktop. So wherever it is, and then just click on the image. If you want to describe the image, you can, but it's not necessary. This is for screen readers. So anybody who has, how do I say it? Any visual impairments or challenges, the screen reader will automatically say, this is an image of a lenticular cloud. So if you want to describe the alt text, you can do this. So this is an image of a lenticular cloud. Check this out. During a volcanic eruption, right? You don't have to include it, but it's just nice for our friends maybe who have some visual challenges. Okay, here's the deal. The other thing you can do is you can adjust the size of your image. If you click on your image, it's just like you would in a graphics program. You can just grab the corner anchor point and you can reduce or increase the size. And then when you're ready, just click on post your reply and it will embed the image. Now, you can also attach your image. So I'm going to go back to edit and you could do that as well. So there is, okay, let me actually do this. Let me just say done. Let me try this. Let me delete it. Let me do this again. Okay. Hey, students, please see the attached image of a lenticular cloud, right? And then basically so because it's not my own image, I access the image from the Scientific American website, blah, blah, blah. So you want to cite your source. But if you click on this little paper clip that says attached, I'm going to go to my desktop. And okay, let me get rid of this thing just for a second. Okay. Let me go to my desktop right here. Oh, there we go. I don't know why it's not letting me do it. Anyway, let me go to this PC. Anyway, it should be on my desktop. Don't know why I can't access it. But anyway, you just find your file and then just open it and it would attach it. Okay. So you can also attach your file as well and then post your reply. In my humble opinion, I think it's just as easy to embed your image. It just makes it easier for folks to see. But if you have any questions about this, just let me know. And also, trust me, we'll take time to talk about clouds. There is also something I'm going to embed here. There's a really nice video series from the University of New Mexico. This person is named Mel Strong. Let me show you what the videos look like really quickly. Okay. Just, oh, go ahead. Yes.
So for this, we just post a picture of a cloud and then explain about
Like what you think it is. How, like what you think is this? Does this look like a cumulus, a cirrus, a stratus cloud, an alto cumulus, alto? Yes. And then also talk about like where, when and where did you take the photo? Again, you can use cloud photos from the internet, but my preference is make it your own, use your own photo. You don't have to cite yourself. You can just say, oh, this is a picture I took while I was in the plane and we were getting ready to land in Guadalajara or whatever. I mean, absolutely. Or I took this picture when I went to the beach, last month. This is Huntington Beach in, May 2024. I think these are blah, blah, blah clouds. Can anyone help me? What do you all think? Really, I'm not looking for perfection, right? I'm not looking for perfection. Just give it your best. Give it your best try. Okay, so let me show you though. Okay, so Mel Strong clouds. Okay. There's gonna be, oh, I love it right here. This is kind of a fun thing right here. Okay. All right. Yes, there's gonna be, okay. Harbor Freight, you already got me. You devils, you. No, anyway. I know I'm weird. I actually really like just like wandering the aisles. I have no idea. Like I don't have a wood shop or I don't know how to TIG or MIG weld or any of that stuff, but I'm just like, it's super cool. I don't know. I'm weird like that. I don't know if anybody else is weird like me, but okay. So good. Yeah, it's just kind of fun. And there's always stuff. I can't tell you like how many little like extra bits and parts I've gotten. Like I'll use this someday, and someday hasn't come yet, but maybe it will. Maybe after I retire or something. Anyway, I'm going to also embed and post this video. We will watch parts of this video in class. But if you just go to YouTube and just type Mel Strong clouds, in my humble opinion, it is a fantastic video. So he's going to talk about like how clouds are named, and like how we give the prefixes alto for mid-level clouds, cirro for high-level clouds, how do clouds form? Oh, there you go. There are your basic types, what we call cumulus, the big puffy clouds, right? The Simpsons, he actually talks about like cumulus clouds are the only clouds they ever have in the town of Springfield on Simpson, and it's true. Okay, what about a mid-level cumulus cloud? That's what we would call an alto cumulus cloud, right? This is pretty cool. And then a very high level cloud, a cirrocumulus cloud. So anyway, I will share this video with you. We will watch parts of it. Here are more cirrocumulus clouds. Oh, how do you tell the difference, like which is which? If you look on the left, you see how the blotchy cumulus clouds are a little bit bigger. Do you kind of see that? And then on the right, they look smaller and the clouds look thinner. So on the left, this would be an alto cumulus cloud. It's a little bit closer to Earth's surface. And then on the right, that's a cirrocumulus cloud. The fact that it's farther above Earth's surface, higher in the troposphere, makes the clouds look smaller, and they're also thinner. And by the way, a lot of our cirro type clouds are actually so high in the troposphere, they're made of ice crystals. Where temperatures are really cold, water is not going to exist in the liquid state. It will exist as ice crystals. Don't worry, we'll come back and talk about it. It'll be cool and amazing. And then, oh, we have all these other prefixes. Like anytime we have the letters N, I, M, B, means there's precipitation falling out of that cloud. So these are thunder clouds, sometimes called storm clouds, cumulonimbus clouds. These are when they form in the summer. Sometimes cumulonimbus clouds can result in severe weather, like severe thunderstorms, torrential rain, strong winds, hail, lots of lightning, sometimes in extreme cases, even tornadoes. So if you've wondered like, hey, what kind of clouds might a tornado form out of? Probably it's going to be a cumulonimbus cloud, especially a stronger tornado that's a little higher on what we call the EF, or enhanced Fujita scale. And all this stuff we're going to talk about this week, right? And then again, so cumulonimbus clouds can form in the summer. So for example, when you see those big towering storm clouds over the mountains or the deserts to the north or to the east in the summer, that is some of that monsoon moisture pushing in from the Gulf of Mexico, giving us those pop-up thunderstorms that we sometimes find in the summertime in the deserts and the mountains. We typically don't get them here in San Bernardino. Occasionally they'll move into our area, occasionally. And then sometimes, and again, most of these images that Professor Strong includes are actually from the state of New Mexico. So obviously they are colder than most of us in the winter here in Southern California. So they can also happen in the winter. And this is actually very heavy snow falling out of a wintertime cumulonimbus cloud. So again, anytime you see that NIMB means there's precipitation, rain, sleet, snow, or hail falling out of a cloud, right? And then he's got like okay, this is a very common cloud. If you're not sure what the cloud is and it looks like this, we combine a stratus cloud plus a cumulus cloud and call it a stratocumulus cloud, right? So this is what we've got, right? And it looks kind of like this. Where they occur at mid-level, right? This is, again, here's like an alto cumulus cloud. Oh, this is June gloom. So by the way, the clouds that we had last week, right? We have cute little names for these clouds in Southern California. We call them May gray or June gloom, or sometimes called the marine layer. Those are stratus clouds. So if you would go out like tomorrow morning, like, darn it, I'm going to go ahead and finish this annoying, irritating, terrible discussion. I'm going to get it off my plate because Professor Heibel is like killing me this summer. I'm trying to have a good summer and he's not letting me live my best life. I'm just going to go outside in the morning and take a picture of the gray skies. Those would be your stratus clouds. These are not my words. These are the words of Professor Strong right here. And yes, he does have a kitty in front of him for all you cat fans. I'm going to show you some adorable kitty photos at the end. They really are cute. And they're really well behaved. So clearly they're not my cats. My cats would be like horrible and uncooperative. So stratus clouds, he actually refers to them as boring clouds. I will not go so far as to say they're boring. I think all clouds have their own beauty, their own unique beauty. But notice how they're very uniform and gray, and there's not a lot of feature to them. They're just kind of flat gray clouds. That is what we have in the mornings, right? So they're not going to last all week, by the way. So the sky conditions are going to get pretty clear. We're going to have higher pressure and control later this week. Temperatures are going to get warmer, and we're not going to have the morning clouds. So I think tomorrow might be another good bet if you really honestly cannot find any cloud photos on your phone or your camera. If you do still have a separate SLR camera, some of you do out there, and you just can't find a cloud photo and you just want to take a photo tomorrow. Absolutely, you can go out there. And if you take a picture of the sky, guarantee you those will be stratus clouds. These are lower altitude, thin clouds. They don't, stratus just means layered. A lot of these cloud names come from Latin, and stratus is just the Latin word for layer. So these are layered clouds. So this is what the marine layer looks like. The June gloom, the May gray, moisture pushing in from the Pacific. Now, if we get precipitation out of a stratus cloud, and of course, this is the University of New Mexico campus in the winter. So anybody who's transferring to the University of New Mexico, expect hot summers and cold winters because they're in northern New Mexico. They're at a higher elevation. They're going to get, you're going to get all four seasons. I'm just going to tell you. And again, very flat gray clouds. Snow is falling out of them. nimbostratus. You can also get out of your nimbostratus clouds, you can also get rain as well as snow. Again, anytime you see the letters NIMB means precipitation is falling out of that cumulus, or in this case, stratus cloud. Mid-level clouds or your altostratus clouds, they're going to appear kind of translucent. So this is a mix of water and ice that form these clouds, and you'll get kind of a filtered sunlight. So if you've seen clouds that look like this, we get this kind of cloud here in Southern California from time to time. Altostratus, mid-level altitude clouds, right? And then the really high level cirrostratus cloud, completely made of ice crystals. This is what the sun or the moon, it's really cool actually to get photos of the moon at night with cirrostratus clouds. And you kind of see this, it almost looks like a little rainbow. You kind of see this faint little halo around where the sun is. These are sometimes referred to as sundogs, or at night, you know, we have rainbows in the day, right? And moonbows at night, right? You'll get this kind of little halo effect of the light that's kind of refracting through the ice crystals of a cirrostratus cloud. So anyway, and then these are just plain old icy, wispy, high level cirrus clouds. So we get these clouds a lot as well. So these cirrus clouds are almost always made of ice crystals. And then see how they have almost like they have little tails. Sometimes they're called horse tails or horse manes. You're not going to get precipitation out of these clouds, by the way. It's too high up. So even if precipitation is trying to fall out of these clouds, it'll evaporate before it reaches Earth's surface. So anyway, so check it out. Have fun. Oh, here are some of those lenticular clouds, those kind of special clouds, right? And then he explains how they form, especially in areas like New Mexico or Southern California that have mountains. And yes, they really do look sometimes like UFOs, right? They're very cool looking clouds, lenticular clouds. And then we have other clouds that are associated in this case with like cumulonimbus clouds. They're called mammatus clouds, and they kind of droop down a little bit. This is typically where you have like severe weather occurring. And I want to show you one other cool cloud really quickly before we go. But for those of you who are like, I want to see his cute cats. So here's the end of the video, and he's got such an adorable, look at this, looks like a beautiful Siamese kitty. He's so cute. So at the end, he kind of lets the cats wander and do their thing. And this almost looks like a Japanese bobtail. I can't quite tell because the kitty is just sleeping in its bed. But this reminds me of a Japanese bobtail cat I had once named Mika. She was, or Mike Nico. She was so cute. She was such an adorable kitty. Anyway, so one other cloud. So and then, oh yeah, field trip. So let me just say this, stay tuned, Jose. So yes, I appreciate that field trip question as well. Check this out. Maybe if some of you have taken photos of wildfires in our area, let me just show you this. Sometimes they're called pyrocumulus clouds, or sometimes called flammagenitus clouds. Let me just show you some images here. This is a little graphic from how they form from the Los Angeles Times, but let me see if I can, here you go. This one is, so right here. So we sometimes will get what are called pyrocumulus or flammagenitus clouds. This is literally fire weather. This is where a huge conflagration, a giant wildfire will actually create its own weather. So if I can show you this really quickly, here we go. Just trying to find my little, okay. So you have lots of heat from the fire, and which direction does hot air rise? Which direction does it go in the atmosphere? It's going to go up, right? So it's going to rise almost vertically in this case because it's very hot air. Hot air is going to rise in the layer of the atmosphere we call the troposphere because it literally weighs less than the colder air around it. Here's another interesting thing. Fire produces a lot of smoke. And you're like, duh, professor, I already know hot air rises, fires produce smoke. Tell me something I don't know. Well, let me see if I eventually land on something maybe you don't know yet. So fire produces what's called a lot of aerosols, particulate matter, little teeny tiny solid surfaces. It's called ash and soot from a fire. Also, when vegetation burns, it releases a lot of water vapor to the atmosphere. So when all that poor, helpless, defenseless vegetation burns, it releases a lot of soot, ash, and water vapor to the atmosphere. Plus, all of that material is rising upwards very quickly. So what we get are the three so-called ingredients that we need to make clouds. So check it out. So to produce these clouds, we get all three ingredients necessary to form clouds, right? The first thing is just water vapor, right? So we need water in the gas state, right? The second thing we need is hot rising air. And then the third thing is, get this, in order for water vapor to condense, it needs to condense and attach itself to a solid surface. Let me say that again. In order for water vapor to condense, it needs a surface, a solid surface on which to condense. Where are we getting solid surfaces? All the ash and soot from the smoke, right? And then finally, we're getting what are called condensation nuclei. Nuclei, there we go. And these are solid surfaces provided by all the ash, soot, and smoke from the fire, right? Those are the three ingredients that we need to form clouds. Enough water vapor, we got to have hot rising air. And the one thing that I didn't say here, but I'll go ahead and say it, is the key is that the hot rising air needs to eventually cool to what is called the dew point temperature. At the dew point temperature, condensation will occur, right? So dew point temperature is literally just where dew will start to form. So let me just ask y'all real quick, what the heck is dew? What is dew? Like, how would you explain it to somebody that doesn't know what it is?
Air droplets.
Yeah, like droplets of water, condensation of water that's coming out of the thin air. And what time of day and where do you typically see dew?
Morning and on vegetation.
I love it. You see it in the morning, it's out on the lawn in the grass. Maybe you see it on your car or vehicles that are parked outside overnight, right? What that tells you is that overnight the air has reached the dew point temperature, or at least it has on the grass and on the car. So again, what has happened? There's plenty of water vapor outside overnight. What tends to happen with air temperatures overnight? They drop, they get colder because the sun is no longer shining its energy on Earth's surface. So temperatures get colder overnight. And if there's enough water vapor, and if temperatures approach and get cold enough to reach the dew point temperature, condensation will occur. And that is where water goes from what to what physical state. What does condensation mean? Okay, so it condenses, meaning it's going from which physical state to which physical state? Love it. Gas, which is invisible, water vapor, dew, becoming liquid water droplets visible, right? The invisible becomes visible. Excellent. Water vapor becomes liquid water. And here, what we're talking about is where that occurs in the atmosphere, in the troposphere, where there's enough water vapor, where there are enough little solid surfaces for that water vapor to condense, right? And then the temperature gets cold enough, dew will start to form higher in the atmosphere. That's just a fancy word for condensation will occur to produce clouds. And in this case, these are the kinds of clouds that we get. And they are just simply referred to as pyrocumulus clouds. So they're basically cumulonimbus clouds, like storm clouds. And the reason they're pyro is the prefix is because they're associated with a fire. So they're a pretty rare cloud, but they do form in our area along with those really rare lenticular clouds. So if you all want to talk about this, a couple summers ago, what are we now? We're 2024. In 2022, or maybe it was 2021 when I taught this summer class, I had shared a few photos of this from where I live in the San Gabriel Valley. We just happened just like a couple miles north, there was like this huge like pyrocumulus cloud forming. I'm like, oh my God, I'm going to share this with the students. And actually one of my other students actually he either lived in Covina or West Covina, just down the street from where I live. And he was like, hey, I swear I'm not copying off you. These are my own photos, but I also wanted to include my pyrocumulus clouds. And I thought that was really cool. So include whatever you want. It can be the June gloom, the stratus clouds, or maybe you took some photos out of an airplane window and you think, oh, maybe these are cumulus clouds or whatever. Share it. And again, you will get credit. Just give it your best guess. Even if you're like, hey, students, I don't know if this is a altocumulus cloud or an altostratus cloud. I don't know. I think it's maybe one or the other. Can somebody help me out? But here's my picture. Here is where it was taken. Here's when it was taken. So I really, to the best of your abilities, try to use your own personal photo. And this will help you on some of those questions on assignment 6. I promise it really will. Okay, anyway, so check it out. But it's pretty crazy stuff. Hopefully we don't have too many. I know they have a pretty big fire in Northern California right now. So hopefully we don't see anything like this anytime soon. But you know, one of the issues that typically follows a really wet winter, so we had 2 wet winters in a row, is now there's a lot of vegetation out there, including a lot of invasive grasses and weeds that will become very flammable because now we're getting into our summertime dry season because that is our climate. And so we'll see as this vegetation starts to dry out, some of it could catch fire and burn, especially if we start to get high winds like those Santa Ana winds we had talked a little bit about last week. Anyway, let me know if y'all have any other questions about this. But anyway, can't wait to see your cloud photos. Anyway, reach out if you have any technical questions, and I'm totally happy to talk to you about that. Anyway, I wanted to spend a little bit of quality time on this one, and also just kind of remind you, like, now, how do I embed photos? How do I attach photos? Give it your best. Okay. So again, just to the best of your abilities, try to get this one done this week. And all you need to do is just reply to a fellow student. So it's super easy. This time it's just one student, and you can reply with whatever. Maybe they're not sure. Maybe they've asked a question. Hey, students, can you help me with this? I don't know if this is a cumulus or a stratus cloud, or maybe it's a stratocumulus cloud. Maybe give them a little bit of help. Or, hey, I think you're right. I think that really is an altostratus cloud, or whatever the heck or I think your cloud is worthy of being in a coffee table book or a calendar. Totally. Yeah. Talk it up. I mean, praise your fellow students. You all are doing wonderfully so far. Your comments have been nothing but kind and supportive and conscientious. Keep up the excellent work. Just reach out if you have any questions. Oh, yes. There's always one other thing with me. We are in the age of conspiracies, right? And conspiracy theories. And people will talk about chemtrails. Just please know scientifically there is no such thing as a chemtrail. Now, one thing though, so these are contrails, right? So yeah, so So students will be like, those are so you all know what the conspiracy theory is, right? With chemtrail, like, oh, the government is trying to control us. Either they're trying to make us all docile sheeple, and meaning that we're all, they're releasing chemicals to make us compliant, and do the government's bidding, or the government's trying to poison us and shorten our lives so they don't have to spend money on us anymore. Like, the more people they kill off, right, the less money the government has to spend to support them. And it's just like, can I just tell you this? It's insanity, man. First of all, here's where I say people like to have it both ways, and I'll move on. I'll get off my soapbox in like 30 seconds. Okay, 60 seconds. So sometimes the very same people who are like, the government is useless, they can't do a damn thing, they can't do anything, are the same people who suddenly endow the government with all these superpowers, like they can control all of us with mind control. I'm like, really? Well, how can you have it both ways then? Either the government can't do anything or they can do everything, but they can't do both. You know what I mean? So anyway, it just doesn't, it's there's a flaw there in that philosophy. Anyway, so they are contrails. If you want to include this as your photo, yes, it is absolutely true that jets create these, and these are called contrails. These are actually cirrus clouds. These are actually human-made cirrus clouds from the exhaust from jets. So jets fly towards the upper portion of the troposphere, which is in the area of high altitude clouds. So if you want to include contrails as your photo, yes, please do. Absolutely. Because again, what's coming out of the exhaust of a jet? Okay, it is true, by the way, there is a little bit of pollution here, I will just tell you. Right, so we can't forget that. So see, there's a jet right here. Okay, so boop. Okay, so what's coming out of the jet of an airplane? Like, what is coming out of the jet exhaust? And then I want to get your question, Mr. Christian. So, okay, so first of all, it's exhaust, which is going to include what?
Emission.
Okay, definitely emissions. So now don't say, I will make it my job to figure out like what is the overall carbon footprint of flying. It's actually not the majority. Most of the carbon emissions on planet Earth are actually coming from mobile devices, like, again, trains, trucks, cars, right? Stuff on the ground, right? Planes do contribute to carbon footprint. So yes, definitely carbon dioxide. Could there be any particulate matter coming out of the exhaust as well? Yes, just like on any vehicle, anything that burns a petroleum product, whether it's kerosene, diesel, gasoline, or in this case, jet fuel. So here are the condensation nuclei. Do you think there could be some water vapor released at all? Absolutely. A water vapor also comes out of tailpipe exhaust, right? Whatever fuel it's burning, right? So we're releasing water vapor and condensation nuclei. And if there's also enough additional moisture at this altitude of the atmosphere, then you'll get these contrails. You'll get cirrus clouds that form. Now, here's the deal. Like in this photo, where the cirrus clouds seem to be hanging around for a long period of time, that means the atmosphere is pretty moist at those high altitudes. Sometimes, and this is pretty cool, have you ever seen a plane flying and the contrail just like only appears just for a very short time and then it disappears? It's kind of like following the plane and the contrail disappears very quickly. What that tells you is the atmosphere is very dry. Now, if you're a conspiracy theorist, you're like, oh, well, no, professor, that's not right, because the government has done something in this picture. And then, or I had a student ask me one time, they're like, well, then why do contrails disappear sometimes, or you don't even see them at all? I'm like, oh, well, the atmosphere has a different moisture. And the student just wasn't going to buy that. Like, look, I did my best as a scientist to say, no, the atmosphere is just very dry. And sometimes you get very short lasting contrails or none at all. It just tells you that the atmosphere is super dry. In this particular photo, the atmosphere is pretty moist, right? So those contrails are going to hang around. And then why do they get spread out? upper level winds, like the jet stream. We call those geostrophic winds, kind of spread them out over time. Okay, a couple questions. Mr. Christian first, and then Harry. Yeah.
My curiosity was, for me, it's just kind of simple.
Yeah.
I never seen this as a child.
And here's the deal.
I mean,
You
that degree.
okay, two things maybe, or three things. First of all, maybe you just, how do I say it? Maybe as a kid, your attention was more focused on the ground, like, cause when you're kids, you're like, you have your like more intimate associations.
I'm
And
pretty sure I would remember all that crazy.
And then here's another thing as well. There's just simply a heck of a lot more air traffic now. I mean, if you compared like air traffic even a decade or 2 decades or 3 decades ago, there's just simply a lot more air traffic. Now, I know this will be hard for some people to believe. Believe it or not, overall, airline tickets are much more affordable than they were even 20 or 30 years ago, right? 30, 40, even 50 or more years ago, flying was really just for the privileged 1%ers, right? Nobody could afford a ticket. It was just crazy. People had to drive or take a train, right? Now taking a train is actually really expensive. I know, riddle me that one. Anyway, whatever. Because we only have basically one train company these days called Amtrak. We don't have, anyway. But we have lots of airline traffic. So we have more air traffic than we've ever had, and it's probably just going to keep growing. So by the way, those of you who are engineers, maybe try to crack this nut, try to figure out how to make electric planes. That is the next frontier, by the way, trying to make planes that will fly with an equivalent distance and airspeed that are all electric. It's not impossible. It's just really hard. So I want some of you to become engineers. If you're not going to become geographers, right? So maybe not the most satisfying answer. I'll try to give you more compelling answers too. So thank you, Mr. Christian. I appreciate it. Mr. Henry, question.
Yes, question, like, since you were talking about airplane engines.
Yes.
But isn't it also like when airplanes flying very high altitude?
Yes.
Doesn't like the engine, the fan blade sucks up the air and.
Yep.
And that's what pushes the plane too?
Absolutely. And then
be like not polluting the air.
Well, how do I say this? Anything that burns fuel, combust fuel is gonna have pollutants coming out of the tailpipe. Now, planes are more efficient. Planes are in general less polluting than they were in the past, but how do I say it? That technology hasn't moved as quickly as it has for ground vehicles, right? Like trucks and trains and cars, right? Right. Or if we could, and again, this really is the next frontier, or maybe even kind of a hybrid engine, if you will, right? Probably what we'll see is maybe hybrid approaches. That means like gasoline and electric engine, or sorry, jet fuel or aviation fuel and electric motors, probably for short haul flights, maybe like with props, right? Propellers. And then maybe we'll get into the jet engines a little bit later. So stay tuned, right? Anyway, some of you really, this is why I want some of you to be engineers, right? Figure these things out. So yeah.
Have you ever heard somebody calling a volcano eruption pollution?
Oh, so natural pollution. Yes. Yes, there is natural pollution. So lightning sparked wildfires that are not caused by people or volcanoes erupting. Yes, those are actually natural sources of pollution. Absolutely. Yep.
I think that's a conspiracy too.
Oh, okay. So
no,
I know
not that volcanic eruptions are not polluting, but that
right.
humans have polluted more than what natural causes.
Yeah, and actually we'll talk about that. We'll talk about like anthropogenic, like human caused climate change versus like natural climate change. So people say, well, is it one or the other? I say yes. Yes to what? Both, right? There's natural climate change and then we human, think about it. There are 8 billion of us and counting, doing our thing. That's bound to have an effect on the atmosphere. We'll talk about that. Like what, again, scientists, right? What's the evidence? Show me the evidence. Okay. And we'll do that. All right. So anyway, check it out. Have fun. Enjoy. Right. Okay. It's pretty cool stuff. Okay. So here is the deal. All right, so let's do this. Let's go back to, and then again, use those announcements. So you got all your extra help and all this good stuff right here. Let me just show you a couple things. You can use the videos. Okay, great. We can look at the textbook. Okay, great. That's wonderful. But we can also look at the PowerPoint slides. And let me just show you all something really quickly here. Let me open this up and we'll say just once. Okay. Hopefully you all can see this. Let me stop sharing this with you. Let me share it with you again. Okay, I'm going to come back to the PowerPoint slides. Okay. I have to update the discussion. I will do that. Okay. So a couple things. All right. So I will draw just a few things on the board and all that good stuff, but just a couple quick things, and then we'll take a nice, well-earned break. Let me make this a little, let me see if I can make this a little bit bigger right here. Okay, cool. All right. A couple things. So parallels of latitude. So I did a really lousy job on the board, and I think I was like taking you guys like my normal 20 minutes over, and like, oh man, and I thanks to everybody who was able to stay. I'm going to do my best not to do that to y'all anymore. But this is, if I were like some of you in this class an artist, because I know some of you are graphic art majors, or some of you, even if you're not art majors, you can actually draw. And that is not me, unfortunately. So this is what I was endeavoring to do. And we'll look at Google Earth in a moment as well. So remember, latitude is all about a couple things, right? Now you can read it here. Yes, that's great. That's wonderful. But let me just do this. Oops, sorry. Those kitties are too cute, but we'll look at the kitties later. Okay. Anyway, maybe I'll do like share your pet photos. If you don't have pets, maybe you have plants, or maybe you have a pet rock, right? Or anyway, whatever, right? Okay. So just a few things about latitude. Okay, so first of all, latitude is all about north and south. So capital N for north, I'll just put it here one time, and south, right, of the equator. Now, you don't really need to capitalize equator, but I'm going to capitalize it for emphasis, right? So remember, this is just our 0 degree of latitude. Okay. So it's all about north and south. Okay, so here's my question to you, and then I'm going to get to the parallel thing in just a moment. How do I ask this question? Okay, let me just ask by asking. What are the units of measurement we use for latitude? Like, what do we always say when we report location and latitude?
Decimals.
So we could say decimals, and I love it. Degrees. Yes, we can sometimes use decimal degrees. Oh, sometimes we can use what are called degree, minute, and second. And I'm going to mention that because you have I think 1 or 2 questions about that. Okay. I love it. So we use angular degrees to express location in latitude. So just remember, it's kind of like we are using the world's largest protractor and we're measuring degrees with respect to the center of Earth and the equator. Okay, so we use angular degrees. Oh, I got to turn off my, like, what is that sound? Oh, I forgot to turn off my email. Okay, all right. I'll go back and do that. So we use angular degrees to express location. Now, we will also use angular degrees to express location in longitude, right? So we always do that. So now here's my next question. What is the angular range for latitude? What's the minimum? What's the maximum? Y'all tell me.
0 to 360.
Ooh, I love it. So we're definitely going to start at 0. So there you go. I love it. Okay. So the angular range for latitude, oops, let's try spelling it correctly, is 0 degrees. And that's what we call the equator to how much?
90 or 180.
Ooh, so which one is it? You're right. It's either 90 or 180. Which one is it for?
I'm gonna go with 90.
I love it. Yes, 90 degrees. We're going to get to that 180 in just a moment. Okay. Okay, we'll get there. Okay, so it's going to be to 90 degrees north. And what do we call 90 degrees north? That is just simply, it's a point. It's as far north as we can get. And it's one of our special latitude locations. It's called the
North Pole.
North Pole. Love it. We're going to get to the Arctic Circle in just a moment. Okay, to satisfy all. Okay, so that's going to be the North Pole, 0 to 90 degrees north and 0 to 90 degrees south. And we just simply call 90 degrees south the South Pole, right? The other one, right? The South Pole. So 0 to 90 degrees is our angular range. Okay. Now here's my next question. Why do we call parallels of latitude parallel? Literally because they are, right? It's just because, right? So it's because every single degree of latitude is parallel to the next, to the next, to the next. And remind me again, what do parallel lines do and what do they not do?
They never touch.
Right. They're never going to touch. They're going to maintain the same distance apart. So absolutely. So each degree of latitude is parallel to the next. This means that each degree of latitude is equal to the same distance everywhere on Earth. And how much is that? Because I think I promised you, like, I don't know, like early last week, and then we never did the mathematical calculation. Like, how much is each degree worth?
15 degrees, same as the.
Ooh, I love it. I know what, did you say 15? I know exactly what you're thinking. Hold that thought when we get to longitude and time, which we're going to do today, by the way. We're going to do some time calculations. I know that's assignment 2. We're going to do that today. I promise. But how much distance does each 1 degree of latitude cover on Earth's surface? And then I'm going to show you how we calculate that. And it's totally okay if you read a little bit of some of the text. And this is like a real wordy image that you see on the board right now, but it'll help you.
A couple hundred miles.
Ooh, okay. So it's less than a couple. I like where you're thinking though. It's not nothing, but it's less than a couple hundred miles. So each degree of latitude is worth how much distance everywhere on Earth, because they're all parallel. They're all the same distance apart. So check this out. All right. So think about it, right? Okay. So each 1 degree of latitude everywhere on Earth is equal to 111 kilometers, or if you prefer English units, 69 miles. And so you're like, where the heck did those numbers come from? You know, and especially if I were you, I'd be wondering the same thing. So it's actually down here, but how we got that is you take the circumference of Earth, right? So remember, that is 40,000, a little more than 40,000 kilometers, right? Or 24,900 miles. And then how many degrees are there if we go all the way around Earth in a full circle? How many degrees? That's 360 degrees, right? If we go all the way around the circle, that's 360 degrees. But that's also what a circumference is, right? Circumference is all the way around Earth, either around the equator or from pole to pole back to pole, right? All the way around is the circumference, which is equal to 360 degrees. So to calculate that, take 40,000 kilometers and divide it by 360 degrees. right? Or take 24,900 miles and divide that by 360 degrees, and then you're going to get 111 kilometers per degree. Or 6, did I say 260? Okay, just kidding. Let me see if I can fix this really quickly. Okay. So here's what I do, because I don't know what, I haven't figured out how to go back into the Zoom tools and fix it. Thank you. Yes. 360. Thank you. Thank you. 20, because yeah, you would have been like, Professor, I don't know what you're doing right here. But anyway, 24,900 divided by 360. Thank you. And you'll get about, if we round it to the nearest whole number, about 69 miles per degree. I always like to show you like, where does all this stuff come from, right? Like where I have written here, right? In the text, right? You're like, oh, okay, that's where we get it. Okay, here is the other thing, right? I got to show you this as well. So in addition to telling us north or south location relative to the equator, latitude is also helpful for our discussion on the topics of Earth, Sun, relations, and seasons, basically solstices and equinoxes, which is a little bit of assignment 1 meets assignment 2, right? So, okay, so far so good. So they're all parallel, 0 to 90 degrees. Oh, here's the deal. So if we go 1 whole degree, right? So we go from 34 degrees to 35 degrees, we're going to travel about 111 kilometers or 69 miles. Here's the thing. I don't know about you, but that's a pretty big distance. Like that is like more than an ultra marathon, right? That's pretty, even if it was completely flat, that is a really long distance. I don't know about you. Maybe if you're driving, that's not such a long distance, but if you're on foot, that's a pretty long distance, right? So what I'm telling you is, can we be more precise than whole degrees? What do you think? Yes. And that's where we can use decimal degrees or this concept of degrees, minutes, and seconds, right? Degrees, minutes, and seconds. So let me just write, this is where I'm going to write some stuff on the board. Okay. I think I'm recording right now. I guess I should be sure. Yep. Looks like I'm recording. Okay. So I'm going to temporarily stop sharing, if that's okay. I know sharing is caring. I do want to be caring and I do want to be sharing with you all, but I want to write some stuff on the board since we have use of the classroom. Oh my God. Okay. And then we'll get into longitude in a minute and then time and all that jazz. And then, okay. So don't hate me because I'm gonna shift off of this right now. So if you miss anything, remember I'm recording right now and I swear I'll help you. If y'all want to get a photo, you can do that as well. So we're good. We're great. Okay. I don't want to make anybody mad. Like, Professor, I hate you. You suck. Okay. I know. I probably do. All right. All right. So let me do this. Let me spotlight this for everyone. Okay, let me temporarily mute this. I'm going to pull up the screen, so it's going to make a little bit of noise, right? It's going to get exciting. Okay. And let me see if I can do this. Let me just tighten the zoom just a touch. Okay. So let me just go here. Okay. Perfect. All right. So I'm just going to write a couple things on the screen. I hope that's okay with you all. All right. So check this out. This is pretty cool. So let's say, because they're all parallel, let's say we go from 34 degrees north, which is where San Bernardino is located approximately. And then I'm going to ask you all for our 7 key or important parallels of latitude. So let's say we're just going to go this 1 degree, right? So this is 1 degree of latitude. And this is going to be equal to approximately 111 kilometers or 69 miles. That is the distance. And that's only 1 degree of all the degrees of latitude that we possibly have on Earth. So even though it's just 1 lousy little degree, it's still a pretty big distance, right? It really does show us that Earth is pretty large, right? All things considered. Okay, so think about it this way. If we're going to use terms like accuracy and precision, let's talk about precision. if we're plus or minus 1 degree, I don't know about you, but that does not seem very precise. So imagine, let's think about it like maybe in militaristic terms, and we're going to be targeting with, let's say, a rocket. So let's say, or a missile. So, and so we're going to have our enemy in sight, and whoopsie, we were off by 1 degree. Oh my God, we just struck a downtown area and we killed like tens of thousands of civilians. Whoops, my bad. Well, we don't want to be doing that, right? We really, really, really don't want to be in the business of being off plus or minus 1 whole degree. Okay, if you want to think about it in humanitarian terms, let's say we're going to do a food drop. We're going to use parachutes and we're going to drop in some food and water for a starving village. Whoops, we were 1 degree off. Those poor, desperate, starving people on death's door. Guess what, people? You're going to have to walk through the desert another 111 kilometers. That ain't no good. I don't know about y'all, but that is not good, right? So we want to be more precise than that. So we can either break this up into decimal degrees, or we can use this concept of what's called degrees, minutes, and seconds. So check this out. The concept borrows from clock time. Okay, so hear me out on this one. All right, so check it out. So in 1 hour of clock time, how many minutes are there? 60 minutes. In 1 minute of clock time, how many seconds are there? 60. So you're like, okay, I got this. 1 hour of time, 60 minutes. One minute of time, 60 seconds. Use an analogous concept for degrees of latitude and degrees of longitude. So check this out. For each 1 degree, right? Remember that little circle here just means degree, right? So for each 1 degree of latitude or longitude, right, there are what we call 60, and then we use like a little, what's called like an apostrophe, or it's a single prime mark. This just means minutes, right? So there are 60 minutes, not of time, but of angular measurement within each degree. Furthermore, like distance, right? Think about distance. Yes, I love it. Furthermore, right, for each 1 minute, right? Remember, that is a minute of latitude and longitude. I'll get out of the way so you all can read this, right? There are, I should say, there are, almost like a quote mark, a little double prime. See how it kind of looks like a little quote mark right here? And this is what we say by seconds. So it's like this, right? So for every degree, there are 60 minutes, right? So in each 1 degree of latitude or longitude, there are 60 minutes, right? And then in every minute of latitude or longitude, there are 60 seconds. So it's just a way to be more precise. It's just a way to be more precise. So if we split this into 60 little smaller segments, we already would be much more precise. If we were only plus or minus 1 minute of latitude and error, that would be much, much closer to the target. And if we were only off by 1 second. So if you're like, well, what would that look like right here? So let me get out of the way for the Zoom audience. Okay, y'all can see that right here. Let me just pan the camera over a little bit. Let me see if I'm going to actually go, yay, I actually went the right way. Normally I go completely the wrong way. And I'm focusing somewhere like on the back wall of the room, and students are like, what are you doing, man? Anyway, so let's say we do this. Let's say we go from, let's go look at a minute. So let's go from, let's say 34 degrees, 5 minutes north to 34 degrees, 6 minutes north. So this is only going to be 1 minute of latitude. All right, that's what we mean by a minute. So how many kilometers or miles would that be? Like, how would you calculate that? So if a degree is 111 kilometers or 69 miles, what would a minute be? What would you do with those values? How many minutes are in 1 degree? 60. So what would we do with those values? So if in 1 degree of latitude, there are 111 kilometers and 69 miles, how are we going to calculate a minute? Like what?
1.9 miles.
Ooh, okay. And then like, so what did you do with the 69?
That converted from, well, it's a minute, so it's 60 seconds.
Yes.
Second is about a mile, and 69 will turn it into a minute, 1.9 miles.
Okay, so it's definitely going to be just a little more than a mile. Yeah, just divide these by 60. Yeah, right on, right? So we're going to take our 111 kilometers, divide it by 60, or our 69 miles, divide it by 60, and what do you get? Like, how many kilometers would that be? How many miles would that be? If you got a calculator or a phone in front of you, how much is that going to be? Let's do this. We'll round it to the nearest 10th this time. So, but you're right, Mr. Manuel, yes, yeah. So if you do that, what do you get in kilometers? What do you get? And this is just showing you precision. It's all about precision, right?
1.15
I love it. And that's,
miles.
that is miles, right? So it's like around 1 point, if it's 1.15,
Yeah.
it's about 1.2 miles, or in kilometers, it would be how much? Just to get you all to embrace the med.
It's over 2 kilometers. A little under 2 kilometers.
What do you think? It's pretty close. If it was 120, it would definitely be 2. So it would be a little less than 2 kilometers. So what do y'all get? See how mean I am making you do all this math?
1.85.
I love it. It's about 1.9, right? If we round it, right? That's more like it. Now we're a lot closer. And then if we go to seconds, we're going to divide 1.9 kilometers or 1.2 miles by 60. And then we're going to get within a matter of feet or meters of the correct answer. Ooh, I love it. I saw in chat. I love it, Andrea. Yes, thank you. 1.85 kilometers. Thank you. I appreciate you. Yes, fantastic. I love it. Okay. So, and again, that is what we would do. So again, if we would do something like this, what if we get into 1 second, right? And then this is how we would write it. So let's say we do this. Let's say we have 34 degrees. I don't know. I'm just going to totally make this up. 10 minutes and 41 seconds north, right? And then we're going to go just 1 second farther north, right? So this is going to be equal to 1 second of latitude, right? We use a little quote mark, like a double prime. Then we're going to be 34 degrees, 10 minutes, 42 seconds north. Okay. So again, that's going to be 1.9 kilometers or 1.2 miles. And then when we end up doing this, if you take what is 1.9 divided by 60? So just somebody does that real quick. We'll just do this last one real fast, just to show you how precise we can get by splitting it into 1 second. And then we'll move on, I promise, because I want to do some Earth Sun related.
0.0316.
Okay, so I love it. So we're gonna get around 0.03, right? So we're gonna get around something like 30 meters, which is a little, how about 1.2 miles? What if we do, what if you do that? Divide that by 60. Okay, I love it, right? So we're going to end up with 0.02 and times 5280. Yep. So we're going to get about 130 meters or about 106 feet, right? Again, that's not nothing, right? And we probably would want to be even more precise from like we would probably want to be within, we would probably want to have like inch or centimeter accuracy. And this is where we can subdivide the seconds into decimal seconds and get even more precise. But now we're within easy walking distance, right? But within 30 meters, a little more than 100 feet, right? So pretty cool stuff. So this is just showing you how much more precise. And we can do the same thing. We can chop up, we can subdivide degrees of longitude also. Any angle into degrees, minutes, and seconds. It's just showing you all about precision. I always like to do this, and I don't always do this with my classes because I like you all so much. Don't tell my other classes where I didn't discuss this in as much detail. Okay, anyway, fun stuff, and it's math, which I know is everybody's favorite topic, and you're like, really? Is that what we told you? No. Okay, all right. Sochi told me that. She's like, no, I didn't. Stop dragging me into these conversations. Oh, no, I had nothing to do with that. I swear. Okay. One time I had a student that, and I felt so badly because I thought I was being so cute and funny. And the student was like, I don't really like it when you do that with me. I'm like, I'm sorry. Oh my God. And I felt like just, oh, it was like one of those cringe-worthy moments. Like, I'm so sorry. I don't mean to embarrass you publicly. I was just trying to call you into the conversation. All right. I'll do it more delicately. All right. So let me just do this. I'm going to ask you all a question and then we'll take a well-earned break. So this is going to help you a little bit with assignment 1 and also with assignment 2. So remember how we said latitude is not only north or south of the equator, but it can also help us with Earth-Sun relations and seasons. Okay, so is it okay if I erase this right here? My beautiful, gorgeous artwork. Yeah, right. Okay. Okay, here we go. Okay, let me just do this. I don't want to speak too soon. The markers are doing great, but I have a feeling they won't last all summer, so I have to treat them gently. All right. So this can help you, those of you who are in the lecture class as well as the lab class, a little bit of assignment 1, but also assignment 2. Okay, and it's going to help us with the what we call the 7. Did I get this right? Yeah. Got all my fingers here right. 7 important or key points and lines or parallels of latitude. Okay, so check it out. So you all already told me this. Okay, well, I'm going to make sure everybody has a globe in their vicinity right here. And don't worry, by the way, the globes make this really horrible racket on the desktop. You all probably figured that out already. Apologies. So if you have a globe in your vicinity and if you're on Zoom and you happen to have a globe at hand, hopefully you're not driving, but if you're driving and you have a globe in the passenger seat, just maybe pull over for a minute. Okay, all right. So, okay. So here's the Earth. Now you all told me that on a globe, okay, so we can make the Earth rotate on its axis, and we know that that takes almost, and we round up to 24 hours, like 23 hours and 56 minutes, right? But what was that other peculiar thing you noticed about Earth on its axis? Like it's tilted, right? So instead of straight up and down, right? Earth is not rotating on its axis straight up and down like this. It's tilted. And the tilt is approximately 23.5 degrees. Now, Earth does precess or wobble a little bit on its axis, like plus or minus a degree or so, and that's what gives us a little bit of natural climate change, right? It precesses or wobbles a little bit. Like if you've ever had a spinning top on a tabletop, you'll see after a while it'll start to wobble like this. Earth kind of does the same thing. But right now, in our current geologic epoch, right, we are about 23.5 degree tilt on the axis. Mr. Henry, question. Yes.
Your turns on, there's on the tilt and.
Yes.
Doing rotation, what if it's a bit, just big this, you know, would it make a difference?
Yes. Let me ask you this question. What if Earth was not tilted and it was just straight up and down like this on its axis? So it's still rotating once every 24 hours. We're still orbiting the sun once every 365.25 days. But what would happen? Or should I say, what would not happen?
there will be no solstice, no equinox.
Thank you. There would be no solstice, no equinox, because why?
It'd be unchanging weather in certain parts of the world because they're not, the tilt has to do with the weather a lot. I know that much.
Ooh,
Like we're about to hit summer solstice on the 21st.
yeah. Oh my, you need to be a geographer or maybe a meteorologist. No, seriously, seriously. I'm not being facetious at all. Absolutely. We would no longer have seasons. We would not have the seasonal rhythm. Everybody on Earth would receive exactly 12 hours of daylight and 12 hours of darkness. The sun would always be at high noon, directly overhead at the equator every day of the
Like
year.
parts where it snows will always snow. Part where it
Yep.
never rains, it'll never rain.
Yeah.
It would just be static.
It would be, yes, we wouldn't have those like the wet and dry and the cold and warm seasons. Yes, we would not have those seasonal changes in weather or climate, right? As we have them right now.
So that would affect, so what he just described.
Yes,
Would that affect like our food supply, like crops?
absolutely. Totally. Huge. And I'm glad that you brought it back. So like what impact would that have on life, especially us humans? Huge impact. Yes. We, species would have evolved differently had Earth not been tilted on its axis, right? Now we would still have winds and ocean currents, but they would behave much differently. Climate patterns would look much different if Earth was not tilted on its axis. Yep.
Would it be like rings of climate around the earth instead
Yeah.
of like specific areas?
It would be more like almost like quasi-parallel, bands of climate from the equator to the
Kinda like how
poles. Yep.
Jupiter looks.
Yeah, almost kind of like, yes, our climate regions would kind of look like the stripiness of Jupiter, if you will. Yep, I love that. I love that analogy. Ooh, I'm gonna have to borrow that one. I'll give you credit though, don't worry, okay? All right, I love it, absolutely. Bye-bye seasons, right? We wouldn't even have that concept in our heads. Maybe we would have what if Earth was tilted on its axis? And you would all be like, oh my God, that would be crazy to imagine that, right? It'd be just like it would be crazy to imagine Earth not tilted on its axis. But because Earth is tilted on its axis 23.5 degrees and it orbits around the sun once every 365 and 1/4 days, we are going to have our changing seasons. Spring becomes summer, becomes autumn, becomes winter, becomes spring again, right? And so on and so forth. Solstices and equinoxes, right? Some climates that have wet and dry seasons. This is the reason why. Some climates that have distinct thermal seasons, hot summers and cold winters. This is the reason why, right? So absolutely huge impacts, and all life on Earth, wind currents, pressure systems, ocean currents are all the result of this, right? This tilt of Earth on its axis at about 23.5 degrees relative to the sun, which is our closest star. And by the way, about how far away is our sun from planet Earth on average? You can
3 million miles.
about 93 million miles. If you don't like miles, you like kilometers, about 150 million kilometers. Now that is the average, because true or false, there is a time of year when Earth is closest to the sun, and then there's a time of year when Earth is farthest from the sun. True. But is that what gives us our seasons? No. And you're like, what? Wait a minute. Whoa. Okay. What if I go so far as to tell you this? When Earth is closest to the sun, it's about 3 million miles or 5 million miles closer than Earth is when it's farthest from the sun. So the difference between when Earth is closest to the sun and farthest from the sun is plus or minus 3 million miles or 5 million kilometers. Yes, technically speaking, Earth overall receives a little bit more energy from the sun when it's closest to the sun, because proximity matters. That's why Mercury receives a hell of a lot more energy from the sun than Earth, because they're a lot closer to the sun than we are. And then Neptune, being so far away from the sun, receives so much less solar energy than the other planets that are closest to the sun. So yes, proximity matters. And then when we're closest to the sun, the totality of Earth receives just a fraction of a percentage more energy from the sun. But sorry for my rhyme here. The reasons for the seasons, cute, right? Super cute, is the combination of Earth's tilt on its axis plus that 365 and 1/4 day orbit around the sun, right? It's all about the tilt plus orbit. That exposes different, here we go, latitudes to more energy from the sun or less energy from the sun, depending on where we are in the trajectory. And you're absolutely right, my friend. In just a couple weeks' time, we're going to be celebrating the June solstice. So yay, right? First day of summer for us in the Northern Hemisphere. And then we got to talk about our friends in the Southern Hemisphere. All right. So, okay. So are you ready for this? All right, here we go. So let's do, speaking of the June solstice, let's celebrate early, right? Okay. So let's have the sun over here. And by the way, so the sun is it's going to sound like I'm talking about somebody in Hollywood here, like a middle-aged star. You're like, huh, we have a lot of middle-aged stars out there. All right. And it's kind of a mid-sized star as well, right? It's about the same age as the rest of the solar system, which is about 4.5 to 4.6 billion years old, right? Why do we call it the solar system? Because the sun occupies more, check this out, more than 99% of the mass of our solar system. Let me say that again. The sun is so supermassive that it occupies more than 99% of the mass of everything in our solar system. So that means all the meteors, all the comets, all the planets, all the moons, all the dwarf planets like Pluto occupy less than 1% of the totality of mass in our solar system. And the sun is so huge and supermassive that this is why all the planets and asteroids and meteors and dwarf planets like Pluto are trapped, are prisoners, if you will, of the sun's gravitational pull. So if you remember that video that I showed you all real briefly, I think it was the Solar System 101 video last week, the Oort cloud, right? That is on the very, 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 very outermost edge of our solar system. That is all the stuff at the outermost edge of our solar system that's still just barely caught up in the gravitational pull of the sun. But that is millions upon millions upon millions upon millions of miles or kilometers away from the sun. So relatively speaking, we're pretty close to the sun. We're not even close to the edge of the solar system. If we were, we wouldn't be here talking right now because we would, right? From our perspective, the sun would appear very tiny and very cold, right? But okay, so here's the sun, right? It's our closest star. So don't let anybody trick you like, wait, is that going to be Polaris or Sirius or Canis Major? Or anyway, it's the sun, right? And we capitalize it because it is our sun. By the way, not every star that you see in the night sky is another planet's sun, but many of them are. Many of them are. So when you look in the night sky, preferably get out of our light pollution here in the city, a lot of those stars, not all of them, but a lot of them that you see are actually stars for other planets. Those are stars that represent other solar systems. Ooh. True or false? Some of those stars that you see in the night sky do not even exist anymore. True or false?
True.
True. How can that possibly be? What the hell, Professor? Why? Okay, what the hell? Why can you still see them if they don't exist anymore? Yes, give an example. And then we're going to, yeah. So
It's the distance that light travels, and distance equals time and space.
I
So
love
for
it.
example,
Yes,
just a short example.
I love it.
If our sun were to disappear right now, this
Yes.
moment as we speak,
Yes,
we wouldn't know for about 8.5 minutes.
you are so right.
Because it takes light at the speed of light to get to us
Ooh.
in that amount of time.
Well, how many minutes is that again?
About 8.5.
Yeah, Yeah, a little more than 8 minutes. I love it. Beautifully said.
Or we wouldn't know if we'd be hanging out with our sun in the sky for 8.5 minutes until it just disappeared.
And then we wouldn't know. And hopefully it would be instantaneous because that's how I want to go. I don't even want to know that I've gone. I don't want to suffer. I know I'm a wimp. I know. I'm like, oh, right. I know what they say in certain like military parlance, pain is only weakness leaving hell, I don't want that. So I'm sorry. I'm just too damn old. I did my pain thing early, right? Anyway, and sorry. I know. I get it. I hear you on that. I know, right? We all gotta like pay to play and all that stuff. But exactly, but you're right. Speed of light is like the universal speed limit, right? Now you can argue and split hairs and say, what about some subatomic particles? Is there evidence that maybe they can exceed the speed of light? Maybe, but that's above my pay grade and I'm not a physicist, but maybe. Anyway, some of you go into astrophysics and you can maybe teach me more about that and dark matter and string theory and all that jazz. But the known speed limit of the universe is the speed of light. Yes, amen to that. We are about 8 minutes according to the speed of light from the sun. So 93 million miles or 150 million kilometers traveling at the speed of light. It takes the sun's light a little more than 8 minutes to reach us through that distance, traveling at the speed of light. Yes, some of those stars that you see in the night sky, we are still seeing light from those stars because they are so many light years away, hundreds, thousands or more light years away. We are still seeing the light energy with our skies, with our eyes, even though they have gone supernova and exploded, who knows, maybe thousands of years ago. But so when you look at the night sky, it's almost like a fossil night sky. We are seeing the night sky, depending on how distant that star is, of what it looked like hundreds, thousands, tens of thousands of years ago. Isn't that kind of a trippy thing, right? So think about it. People will be seeing our sun many, many light years away, a long time after our sun is long gone.
Somebody
right?
far away,
So,
let's just say as an
yeah,
example,
yeah,
would barely be seen our son being born.
correct. Right on. They'll be like, oh my God, you know about this new star?
star.
Okay, not really. It's 4 point blah blah year million, billion years old. Yeah, yeah. Isn't that trippy and weird? So in a way, we're always time traveling. I know, right? Ooh, Henry, yes, question.
Would Alpha Centauri be the closest solar system?
I think you're right. You know what? Somebody look that up. I think
It
you're
is.
right. I think that is our next closest star.
4.2 light years.
See, y'all, I'm telling you, y'all are like amazing. So how many light years is it? Yes.
4.2.
Oh my God, you are man, I love it. So yeah, y'all are like better. Yes, thank you. I think
Something like that.
double check that if y'all like, what is, okay, other than our sun, because your Google search might be a smart ass, like, duh, it's the sun. Hello. You're like, yeah, okay. Other than the sun, I think you're right. I think it is Alpha Centauri, which by the way is not the brightest. So y'all look that up real quick while I'm writing a few things down. So what is our closest star other than the sun? And then what is the brightest star in the night? I think the brightest star might be Sirius, maybe.
Star.
Could be the North Star, Polaris. And by the way, we'll talk about why Polaris or the North Star is our North Star. It has to do with our conversation. But
Finding yourself.
Yeah, it has to do with finding yourself, literally. Finding yourself is a tough thing sometimes, right? Okay, so while you're doing that, so again, closest star, brightest star. Oh, and then look up Polaris or the North Star too, if you don't mind. So just do your search, and I'm going to interrogate you in a minute. Okay. Why is our sun a thing? Why does it emit so much energy? In other words, what is the fuel for the sun?
Hydrogen.
Hydrogen. The sun is totally hydrogen powered, right? It's a thermonuclear reaction of hydrogen, right? H2, and it's a fusion reaction. Here on planet Earth, if you've heard of nuclear power, we split atoms, right? Like uranium atoms, right? To generate a lot of heat, which heats water, which generates steam, which we pass through tubes and it spins turbines, and then the electrons get sent through the wires, right? That is nuclear power, but we split atoms. It's called fission. The sun smashes those atoms together. It's called fusion, right? So if you ever have heard of a nuclear bomb, like what's called a hydrogen bomb, that is basically replicating what the sun does to very dramatic effect. And that would like ruin our whole day. And okay. By the way, the sun still has a few billion with a B. Like how much hydrogen does the sun have? So I always tell you all just focus on finishing this semester, right? Because so you're like, isn't it true that the sun is going to burn out? And when it does, before it goes what's called supernova and explodes, it'll expand to become a red giant. So as the sun really gets to the end of its hydrogen fuel, it'll start to grow and become what's called a red giant. And it will engulf the closest planets, probably including us, our own planet. Which, yes, will definitely be the end of all life as we know it. And that's the end of bye-bye Earth. But all good things must come to an end. But that's going to be a few billion with a B years in the future. So make your mark now, ace this class, live your best life. And if you have kids or maybe even nieces, nephews, cousins, whatever, make sure you do your best to be a good mentor so they live their best lives and then their kids. Anyway, right? So anyway, nothing's going to happen like tomorrow or the next day or even for a couple billion years. All right. Okay. Anyway, I'm just saying right here, but because you have some questions about this. Okay. Now, here's the other thing. And then I want to give you all a well-earned break. So remember, now I am not drawing any of this to scale. Remember, the sun is millions upon millions upon millions of times larger than the Earth. Okay. So just remember that. I want to just prioritize our Earth though, because that's our home. It's the third planet from the sun. And okay, it's one of the 4 terrestrial planets. And okay, so let's look at the June solstice position. Okay, so check this out. Okay, I'm going to draw. Okay, it's going to be a lumpy Earth. Apologies in advance. All right. So we're just going to do this, right? Okay, so here is our Earth. Okay, so here's the North Pole, 90 degrees north. Here's the South Pole. And then remind me, what do we call this imaginary line around which Earth rotates once every 23 hours and 56 minutes? What do we call this again? So what did we say this was again, around which Earth rotates once every 24 hours? That's the axis. Okay, I love it. Okay. And I tried to show, okay, so this is Earth's rotational axis right here. And remember, relative to straight up and down, so I'm just gonna, I'll just draw this, right? So this would be vertical right here. So that angle, that tilt is going to be 23.5 degrees, 23.5 degrees, right? So 23.5 degree tilts, right? On its rotational axis. Okay. And then you all told me, man, you all were like, again, give yourselves a round of applause because, man, y'all are giving me like great information here. Okay. So, and you said that the distance between Earth and sun, and I didn't quite draw my sun correctly here. Sorry about that. I apologize. Okay. So you said this distance was about, on average, 93 million miles, or about 150 million kilometers. So here's a weird thing. So Earth's orbit around the sun is not completely circular. It is elliptical. So you answered this question earlier, but I'm going to ask it again. Well, I'll just repeat your answer because you were correct. You all told me there's a time of the year when Earth is closest to the sun, and then a time of year when Earth is farthest from the sun. So approximately when is Earth closest to the sun? And before you answer the question, it's gonna seem wrong and just bass-ackwards and just not right.
It's winter.
It's like in the midst of our northern hemisphere winter. Earth is actually closest to the sun in early January. I know, I didn't say that wrong, right? Earth is actually closest to the sun during the first week of January. So what we call that is perihelion, right? So Earth is, let me make the P actually look more like a letter P. There you go. P-E-R-I means near. Helion means, well, like the Greek god Helios, sun, right? So it's like double Greek and Greek, right? So this is when Earth is nearest the sun. And again, it's going to seem wrong to us, but that actually occurs around, on or around the first week of January. So, and that's when we're about 91.5 million miles away from the sun, about 147.5 million kilometers away from the sun. So then when do you think we're actually farthest from the sun?
Summer.
During our midsummer. And you're like, that just seems so weird. And that is actually called aphelion, right? So aphelion, this is actually when Earth is farthest from the sun, okay? Farthest from, sorry, okay, I'm trying to write this so you all can read it. And that's going to occur in the first week of July. So like after this class, just after this class is finished, everybody's earned their A+++, and you know, life is beautiful, right? So this is going to occur in early July, right? So like when we're experiencing some of our warmest weather. By the way, if we were in the southern hemisphere, this would totally make a lot more sense to us, but because we're in the northern hemisphere, it just seems wrong. So it is absolutely true. When we're closest to the sun, in totality, Earth receives just a little bit more energy from the sun. And when we're farthest away from the sun, Earth receives just a little bit less energy from the sun. Okay, great. Okay, wonderful. But what overwhelms this is the tilt on the axis plus its orbit around the sun. Now, here's the deal. Polaris, the North Star, was mentioned a few minutes ago. Oh, by the way, so how far away was it Alpha Centauri? Did you all figure that out? Like how far away is it?
4.2 light.
Good, 4 point. So it takes so light from Alpha Centauri, which, thank you, which is our closest star, traveling at the speed of light still takes 4.2 years to reach our eyes. So the light that we're seeing from Alpha Centauri is already 4.2 years old, right? I know, right? Oh wait, what about the brightest star? Maybe it's Betelgeuse. I don't even remember. Which one is it? It's true. I know you all think it's like a movie. It's like actually a star's name. So
Is about to die.
is it
Well,
about?
probably died already.
We just haven't noticed, right? Or maybe it's Sirius or Sirius Major. Anyway, did anybody figure that out? Like the brightest star?
It goes years out.
Sirius Alpha, thank you, is the brightest star. And I forgot how many light years away that is. That's the star, that's one of the stars that really stick, even in a lot of light pollution like we have here in the cities. Again, go to the desert, go to the mountains, go where there's very minimal light pollution so you can actually properly see the Milky Way galaxy. Oh, that is how the night sky should be seen. Oh my God. Anyway, crazy, right? Thank you, by the way. Then another star to be aware of, other than our sun as well, is going to be what we call Polaris. So if we would connect a straight line with the North Pole, it would connect with a North Star that we call Polaris. So Polaris is our North Star. The North Pole, pretty much if we connect a straight line, I don't know how many light years away is Polaris. Several light years away, it would connect with the North Star Polaris. In the night sky, all the stars appear to rotate around Polaris. What's really happening is we are the ones doing the rotating around our own axis because we're all captives and prisoners on planet Earth, right? So here's the thing. The Earth maintains the same 23.5 degree tilt, the same orientation, no matter where it is in its orbit around the sun. That causes the direct rays of the sun to hit different areas of Earth, different latitudes of Earth at different times of the year. If you don't believe me, let me quote unquote prove. Okay. Never say proof in science. Let me give you evidence here. Okay, so check it out. This is going to be our June solstice position. Okay, this is we're going to be on or around the 20th of this month. Okay, and we'll be in class. We'll celebrate. Well, maybe we'll have like some solstice cookies or something like that. Okay, so check this out. Okay, so this is going to be the 0-degree equator. This is going to help us with our important latitudes as well. Okay, so this is, right, this is going to be what we call the most direct insolation. So what we call this, is it okay if I erase these distances now? Again, this is the average distance. It's about 1.5 million miles closer, or 2.5 million kilometers closer at perihelion, and then 1.5 million miles or 2.5 million kilometers farther at perihelion. But this is the average distance. And yes, it takes light energy from the sun a little more than 8 minutes. That is the answer to one of your questions on your assignment, by the way. Okay. And if you know the speed of light, you can do a distance rate time calculation. And if you want to do that, we can do that at the end of class today. But okay. All right. So you ready for this? Okay. So this latitude where the overhead sun, so we refer to this as the overhead sun. It's also referred to as the subsolar point. And at the June solstice, when the North Pole, the northern hemisphere, is most tilted towards the sun, which important latitude do you think this is? Now, remember, I'm not drawing anything to scale. It's just because I'm a really terrible.
I forgot what's called in Greenwich.
Ooh. It's going to be one of our tropics, but it's going to be I love it. The overhead sun at the June solstice, which I think this year is going to be like on the 20th of June, right? We're getting close, right? That is going to be over the Tropic of Cancer, right? Which is, how many degrees north is that?
According to this globe.
It probably just says it on there, but
I'm trying to see about.
you can kind of
Between
estimate.
15 and 30, so it's right above.
It's definitely between 15 and 30. Yep, kind of almost right in the middle.
What's that be? 23.5.
I love it. Everything to do with the tilt. Remember I said this tilt is going to come into play with some of our funny or important or odd sounding parallels of latitude. Yes, the Tropic of Cancer is 23.5 degrees north of the equator. And at the June solstice, this is where the sun would be directly overhead. It's called the overhead sun or subsolar point, right? And so at high noon, at 12 noon, well, I should be careful here. It's not necessarily relates to clock time, but when the sun is highest in the sky, we call that high noon or solar noon. Just like if you're a big fan of Westerns, like we're going to have a shootout at high noon, and everybody's like, and like, how do they know when that is? It's just when the sun is highest in the sky. And if you were at the Tropic of Cancer at the June solstice, the sun would be like directly over your head, and it would make a 90-degree angle with respect to the earth. You would not see your shadow for a moment, right? As the sun is directly overhead. That's as direct as the sun is ever going to get at the Tropic of Cancer. And that's going to happen at the June solstice. Okay, now we have other important latitudes. Let's stick with the northern hemisphere just for a moment. If we go much farther north and we go to 66.5 degrees north, what do we call that? What is 66? And I just didn't draw my sketch very well, but what do we call that important parallel of latitude that's about 66.5? In other words, 90 degrees minus 23.5. Do you see where we're going with this? What do we call this important parallel of latitude? I love it. It's the Arctic Circle. Yes. So this, and it likes its two C's. So this is the Arctic Circle. And then of course the North Pole at 90 degrees north. I'm just going to put it up here. Sorry, I'm just going to erase my little rotation here. So, okay, so here we go. So 90 degrees north, that's just going to be our North Pole right here. And then of course we have our 0 degree equator. All right, I'll just put equator right here. It separates the northern half of Earth from the southern half of Earth, the northern hemisphere from the southern hemisphere. So just remember, the equator is just 0 degrees. It's neither north nor south. It's the origin, it's the dividing line between north and south. Latitude's always about north and south. So now we have our 0 degree equator, 23.5 degree north, Tropic of Cancer, 66.5 degree north, Arctic Circle, 90 degree north, North Pole. We're going to do our stuff in the southern hemisphere in just a minute. But check this out. This vertical line that I drew to help emphasize the 23.5 degree tilt, right? This is the dividing line between daytime. So we're going to have the daylight half of Earth over here. So this is going to be daytime over here. And then on the other side of Earth over here, that side of Earth that's rotated away from the sun, it'll be dark. So it's going to be nighttime over here. What do we call this dividing line between daylight and darkness?
International dateline?
Ooh, good question. Good answer. It's not the it's not the prime meridian or international dateline, which we will get to. And those are important meridians of longitude that will help us understand time a little bit better. What do we call that dividing line between daylight and night? Day and night. Daylight or light and darkness. We rotate through this line twice every day. We call it sunrise and sunset. Ooh, that is our circle of illumination, right? So I'll just draw a little up here. So this is going to be our circle of illumination, right? Yes, this will help you on some questions and answers. And if you're in the lab class, it'll also help you on a lab exercise and a lab quiz, hint, hint. And if you haven't taken lab yet, just keep these notes in your pocket, right? Okay. So that's the dividing line between the day and the night half of Earth, circle of illumination, right? So, okay, now, ready for this? Okay. When you look at the northern hemisphere, right, basically north of the equator, hopefully what you'll see, despite all my my busy sketch and it's all messy looking, hopefully you'll see that way more than half the northern hemisphere is in daylight. The majority of the northern hemisphere is in daylight. Only a small fraction is in darkness. And that totally will make sense when you answer this next question to me. So, which season for the northern hemisphere does the June solstice represent? It's our first day of summer. So I guess right now we have maybe like what we call maybe an illegitimate summer semester, but it'll be legit after the 20th. All right, okay. So almost, right? We're almost summer. So I guess we're still like late spring. Okay, anyway, so absolutely. So this is going to represent summer in the northern hemisphere. So a couple things about that, right? If it's summer, okay, why is it summer in the northern hemisphere? Two reasons. First of all, it's the longest daylight period of the year. Now, you all told me every day of the year at the equator, because the circle of illumination equally bisects the equator. How much daylight is received at the equator every day of the year? 12 hours. Doesn't matter if it's the June solstice or if it's an equinox or the December solstice or what is today? The 3rd of June, right? 12 hours every day of the year. So the equator always receives 12 hours of day, 12 hours of night every day of the year. But as we go north of the equator, more than 12 hours of daylight. So at the June solstice, this is the longest daylight period for the northern hemisphere, right? Longer daylight period means more energy from the sun. Temperatures are getting warmer. Let's call it summer. Here's the other thing. For most of the northern hemisphere, it's also the highest sun angle. The more direct the sun angle, the higher the sun angle, the more sun's energy receives Earth, higher temperature. So it's a combination of high sun angle, long daylight period. Temperatures are warming up in the northern hemisphere, to be careful. Northern hemisphere, that's why we call it summer, right? Now let me ask you one other question. Two more, and then we'll move to the southern hemisphere, because I don't want to be all northern hemisphere biased, right? How much daylight at the June solstice are we getting at the Arctic Circle? 66.5 degrees north. Here's your hint. Notice we're totally on this side of the circle of illumination.
19,
Even more,
21,
even more,
23,
even more.
30, 24.
24 hours of daylight. How can that possibly be?
Oh, yeah.
Because the entirety of the Arctic Circle is on the daylight side of the circle of
The sun doesn't
illumination.
disappear, it just hides for a little
Yep,
bit and then-
sun almost sets and then it rises again. It doesn't completely set and then it'll rise again. So at the Arctic Circle, we're gonna get 24 hours of daylight. And then guess what? North of the Arctic Circle to the North Pole, the daylight period goes from 1 day to 2 days to 3 days to weeks to months. And by the time we get to the North Pole, we're talking 6 months. I'm just put MOS for months. 6 months of day followed by 6 months of night. At the June solstice, the North Pole at 90 degrees, it's 3 months into its 6-month summer sun season, I should say, right? 3 months into its 6-month daylight period. The sun will be, you guessed it, 23.5 degrees above the horizon. And it'll make a circle in the sky at the North Pole. I'll show you a video before we go today. Like we'll be looking at from the perspective of the South Pole, but it would be the same thing if we were at the North Pole. The sun is just going to make a circle in the sky at the June solstice at 23.5 degrees above the horizon. So just, yeah. So crazy. We're like, what the heck? That's preposterous, right? But it's true, right? Now we go into the southern hemisphere. So if it's summertime for us in the northern hemisphere, which season has started in the southern hemisphere?
Winter.
Winter. Think opposite of the summer. I love it. So if we go to okay, I'll do my best, right? So this will be 23.5 south. This is the Tropic of Capricorn, right? The other tropic. Then we're going to have 66.5 degrees south. This will be the other circle, the Antarctic circle. And then, of course, we have our 90 degrees south, South Pole. Okay. So what's happening here in the southern hemisphere? The sun angle, right? Well, at least for parts of the southern hemisphere, we're still getting sunlight. But first of all, we're getting less than 12 hours. And if you look at it, if you look at the portion, if you look at the share of the southern hemisphere in daylight, it's less than half, much less than half. Most of the southern hemisphere is going to be in dark, right? At the June solstice. The sun angle is getting very low. So lowest sun angle of the year for the southern hemisphere, shortest daylight period of the year. And in fact, how much daylight are they getting at the Antarctic circle, 66.5 degrees south?
30.
In fact, it's totally on the dark side. It's on the night side of the circle of illumination. So it's going to be 0 hours. Now, you could argue and you could say, well, it wouldn't be totally dark because like right around the time when the sun would peep above the horizon, aren't they going to have a little bit of twilight? Yes, that's it. A little bit of twilight, but the sun will never rise above the
It's
horizon.
like you don't even see the sunrise. It's
Nope.
twilight for like 15 minutes and then back to
And
complete dark.
it'll get dark again. Yep. And really freaking cold. At the South Pole, they're 3 months into their 6-month dark period. So temperatures are brutal. They're already cold even in the light period in the South Pole. But it's just crazy cold. And in fact, we'll see a video later. I don't want to ruin this for you. There have been temperatures recorded in Antarctica, close to the South Pole, that are actually colder than the surface of Mars. What? That is freaking cold. I know, right? That is cold. Yes, it's true. Okay, right? So, so again, it's going to be at the June solstice, it will be winter, right? Winter in the sun. Because again, I don't want to be all northern hemisphere biased here. But this is why it's all about that 23.5 degree tilt of the Earth, always maintaining the same orientation, orbiting around the sun, that are giving us the seasons, the solstices, and the equinoxes, right? So, so while you all go to, I know it's like super late, and I just want to draw a quick like what's happening at the solstices and equinoxes. So I'll expand on this image a little bit. I'll try to do my best job. And then I want to do a few time calculations with you all as well. We can talk a little bit about open and closed systems, positive and negative feedback systems as well, maybe a little bit about map scale, and that'll help us to finish a lot of the discussion on assignments 1 and 2. And then tomorrow, we'll get into our conversation of assignment. I know we're backfilling from last week, 3 and 4. So we'll talk about the structure of the atmosphere, troposphere, stratosphere, mesosphere, thermosphere, a little bit of chapter 3, assignment 3, and then what happens to the sun's energy when it passes through the gases, liquids, and solids of the atmosphere. And then why is it a very good thing that Earth's atmosphere acts like a filter? In other words, why would we, right, think about this. Why would we not want to be exposed to the totality of the sun's energy? Basically, so we don't all become crispy critters, but yeah, right? That's a non-scientific way of explaining it. But in other words, yay atmosphere. Yay Earth's atmosphere. It might be thin, but it is mighty, and it is mighty important for supporting life on Earth. So we'll come back and do this. I'm just going to temporarily pause the video because I want to give you all 5 minutes so you can stretch, get something to drink, participate in the hydrologic cycle, right? Whatever you want to do, but come back because I want to talk just a little bit more about those solstices and equinoxes, a little bit about like some of the time calculations, because notice it's been all about latitude. I want to talk a little bit about longitude, the prime meridian, the international date line, what happens every 15 degrees, when do we add hours, when do we subtract hours, if it's a certain time in one time zone and day, how do we calculate the time and day in another time zone? Yes. So it's going to be all about longitude. And then again, help you answer a lot of questions on assignment 2 as well. And then we'll just give you a few prelims for assignments 3 and 4, right? Okay, so let me pause the video because I want to give you all a very well-earned 5. So take 5. So I know it's kind of a weird time. So I'll see you like 1:37-ish back here. So let me just pause the video. We'll pause for the cause. Okay, here we go. Now I got to act natural. Okay, right. Yeah. So, okay. So a couple things. This will help us with a little bit of assignment 2. Think Earth-Sun relations and seasons. Yeah, so here we go. So just remember, we got 4 seasons. Obviously, these are just 4 snapshots in the 365 and 1/4 day that it takes Earth to make one complete orbit around the sun. We know the Earth is tilted on its axis 23.5 degrees. So I'm just drawing the most basic bare bones sketch that I could possibly muster in 5 minutes or less. And so every 3 months we have a solstice or an equinox, right? So we have a seasonal change, right? So we're going to go from, let me just scoot the camera over just a touch more. Okay, there we go. Just kind of center that a little better. So we're gonna go from the June solstice on or around the 20th of June. We'll get to celebrate it this year in a couple weeks. 3 months later, we're gonna have the September equinox. And then 3 months later, the December solstice. And then 3 months later, the March equinox. And then 3 months later, we're back to the June solstice, right? So these are gonna be our seasonal changes. And then I've drawn the equator on each of the little Earths, the little globes, to show us what's happening in the northern hemisphere in terms of seasons and the southern hemisphere. So the June solstice, it's summer in the northern hemisphere, winter in the southern hemisphere. The September equinox, usually around the 21st or 22nd of September, autumn or fall for us in the northern hemisphere, spring for our friends in the southern hemisphere, right? So autumn, northern hemisphere, spring in the southern hemisphere, September equinox. 3 months later, we go to the other solstice, right? Now we're 6 months away from the June solstice. Now we're at the December solstice. It is now winter for us in the northern hemisphere and summer for our friends in the southern hemisphere. And then 3 months later, we're back to another equinox. This time it's the March equinox, spring for us in the northern hemisphere, autumn or fall for our friends in the southern hemisphere. And then 3 months later, we're back to the June solstice and we do it again. So where is the overhead sun? Sometimes we call it the overhead sun. Sometimes it's the subsolar point. Basically, it is the latitude on Earth receiving the most direct radiation or insolation from the sun. So at the June solstice, I'm just going to draw it here. Which important latitude did we say was receiving the overhead sun, the most direct insolation from the sun at the June solstice? Which one is that again? Great, that's our Tropic of Cancer. That's going to be 23.5 degrees north. 23.5 degrees north receives the overhead sun. Most of the sun, the maximum amount of the sun's energy at the June solstice. How about 3 months later at the September equinox? Now, I'm going to tell you because I'm trying to show you a three-dimensional diagram here on a flat two-dimensional whiteboard, and it makes it really tough to show what's actually happening at the equinox. So if you can use your imagination a little bit, where is the subsolar point, the overhead sun at the September equinox? It's actually going to be the what? So think equinox. That sounds a little bit like which parallel of latitude? The equator. So think equinox, equator. Awesome. I love it. So at the September equinox, it's the equator at 0 degrees that receives the maximum amount of energy from the sun. The sun is directly overhead at the equator at the September equinox. Okay, we're going to come back to that. All right. 3 months later, we go to the December solstice, and now the most direct rays of the sun are hitting the earth where? Yes, now it's going to be the other tropic. It's going to be 23.5 degrees south. It's going to be the Tropic of Capricorn that receives the most direct rays of the sun at the December solstice. I love it. 3 months later, we're back to another equinox, this time the March equinox. And where is the overhead sun again?
Where?
Say, think about this September equinox. You got it. Once again, it's overhead at the 0 degree equator. So twice a year, the overhead sun, the most direct rays of the sun are hitting the equator. And that occurs at both September and March equinoxes. Now, speaking of daylight, okay. At the June solstice, the northern hemisphere is going to be more than 12 hours daylight, right? It's the longest day of the year. That's why it's called summer for the northern hemisphere. For the southern hemisphere, one of the reasons why it is winter is it is receiving less than 12 hours of daylight, all the way down to 0 hours of daylight. Less energy is reaching the earth in the southern hemisphere. Temperatures are getting colder. That's why it's winter. On the other hand, what's happening at equinox for everyone? So the sun is overhead at the equator. The circle of illumination equally bisects all latitudes. So everybody gets how much daylight and darkness at the equinox? 12. Everybody's equal. So here's your mantra. Equinox, equator, equal. Equinox, equator, equal. EQU, 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 right? So everybody's equal. Everybody gets 12 hours of day. Everybody gets 12 hours of night. Everybody's equal at the equinox. At the December solstice, one of the reasons why it is winter for us is now everybody north of the equator receives less than 12 hours a day, all the way down to zero when we get north of the Arctic Circle, right? On the other hand, one of the reasons why the southern hemisphere is in summer is they are maxing out. Everybody in the southern hemisphere has more than 12 hours a day. And in fact, when we get to the Antarctic Circle, we're talking 24 hours a day. And then the South Pole is 3 months into its 6-month light period, right? So we're really maximizing daylight. That's why temperatures are warming up and it's summer in the southern hemisphere. And then when we go back to the March equinox, it's exactly the same as it is at the September equinox. Sun is overhead at the equator and everybody is enjoying 12 hours a day and 12 hours of night. The only difference separating September from March equinox is spring and autumn are flip-flopped from the northern to the southern hemisphere, right? So in a way, in my humble opinion, equinox is the easier one of the two to remember. But here's the other thing. If you're like, man, I don't know, the June solstice and December solstice, man, it's hard for me to keep all that information straight. Think about it this way. Whatever is happening at the June solstice, the exact opposite is happening at the December solstice and vice versa, right? They're exact opposites of each other. June and December solstice, the seasons, the locations on Earth receiving the direct rays of the sun, the parts of Earth receiving 24 hours of daylight or darkness. It's just the opposite. So is that okay? Hopefully that'll help you to stay on track for those annoying little questions on assignment 1 and assignment 2, Earth-Sun relations and seasons. Okay, now let's do this really quickly, just because you have a few questions. Okay, are you all ready? Okay, this is going to be fun. Okay, super fun, super exciting, and awesome. I'm even going to take actual real questions from assignment 2. So I'm just going to draw a few things on the board. So, and I know you're all like, oh, goody, more wonderful sketches from Professor Heibel. Oh my God, thank goodness I paid all these big bucks to take this class. Okay. In all seriousness, though, let's do it. Okay. So let's do, okay. So this is assignment 2. So question 1 says, okay, 6 a.m. Monday in San Bernardino. What the heck time and day is it in Mogadishu, the capital of Somalia? And we really do hope, and I'm being quite serious about this, hopefully things will improve. Somalia is a little bit in the same situation as Haiti right now. It's what's known as a failed state. The government isn't really governing. And you know that when you probably heard about this phenomenon of Somali pirates in the Red Sea, taking container ship crews captive and demanding ransoms so people can actually support their families. That's never a good thing when even if you have a small sector of the population turning to piracy, or in the case of Haiti, where the country is ostensibly run by criminal gangs and people are being killed and just for seemingly random offenses, that doesn't bode well for an economy or a government. So we really do hope for Somalia and for Haiti. I have to say this, from the perspective of a political geographer, we hope things will go better for those two countries. Okay, anyway, we'll come back and talk about that. But let's figure it out. 6 a.m. Monday in San Bernardino. How the heck do we know what time of day it is in Mogadishu? And then we'll talk about things like the prime meridian and the international date line. Okay, so you have this really fancy, okay, let me go back to the whiteboard here, sorry. So you have this really fancy world map. Okay, great. Well, let me show you a more simplified version of the world map. So let me zoom back over here. So before we were doing all about latitude. Now let's look at longitude. Let's give longitude east and west a little bit of love. Okay. So first of all, true or false? Meridians of longitude are parallel. True or false? So let me put it this way. I'm going to draw them like they're parallel, but are they really parallel on Earth? Let me see if I can show you an image really quickly, right? So think about it. You're like, I don't know. He's probably trying to get us to say false because it seems like he's being awfully coercive here. Okay. Ooh, exactly. I love it. So let me just show you. I'm going to turn this thing on really quickly. Okay, let me do this. Ah, yes. Okay. So check this out. I'm just going to show you longitude. Okay, let me just turn the projector on really quickly. Okay, there we go. Now, let me zoom, let me pan the camera over really quickly right here. Okay, I'm gonna get this thing, make this thing smaller. I'm gonna push it out of the way here, just so it's out of the way. Don't worry, I'm not abandoning anybody in the chat right here. Okay, let me see if I can make this even smaller. Okay, there we go. Just gonna make this like super tiny and put it in the corner. Okay, let me pan the camera up a little bit. I know we're gonna kind of go off the whiteboard a little bit, and that's okay. All right, so on these meridians of longitude, hopefully you can see, even though I know I'm violating the margins here a little bit, how the meridians of longitude are not parallel. They do not maintain the same distance. So as we approach both North Pole and South Pole, they converge, which means they get closer together and they touch at the North Pole and the South Pole. So that's one difference between latitude and longitude. Parallels of latitude are parallel. They maintain the same distance apart. Every degree is 111 kilometers or 69 miles. That's latitude, but that is not longitude. Meridians of longitude are not parallel. Latitude is all about north or south of the equator. What is longitude all about? So it's all about time, which means it's not about north or south. It's about which two directions? East or west. Love it. So longitude is all about time, which means it's all about east or west. And what do we call this important 0-degree meridian of longitude? That's called the prime meridian. Yes, it's sometimes called the meridian of Greenwich, right? Because it runs through a suburb of London called Greenwich. There's an observatory there. And maybe some of you have been, or if you ever go, or maybe you do a study abroad in London, go to the Greenwich Observatory and you can straddle both hemispheres. Yes, it's very arbitrary and what's called a social construct. There's actually no reason scientifically why the prime meridian should be here. It dates back from the end of the 19th century when Great Britain was, the UK, United Kingdom, was a world superpower. So there were two world conferences, one in 1883, another one in 1884, where it was not unanimous, but a majority of powerful countries, including the United States, essentially voted to locate the prime meridian here. But the prime meridian could have been anywhere. It could have been in Washington, D.C. It could have been in Moscow, Russia. It could have been in Tokyo, Japan, or Paris, France, right? Those are actually some places that were other places, cities that were vying for the location of the prime meridian. So it was a historical decision to position the prime meridian here, officially speaking, in 1884. So that means our modern concept of longitude and time actually only dates back 140 years. I know, right? And by the way, it's all about technology systems. We had these two important technology systems called the railroad and the telegraph that demanded a standard system of longitude and time, because we don't want trains arbitrarily arriving and leaving at whatever station time is, and then people miss their trains, or get this, we have horrible fatal head-on collisions, which is what happened a lot back in the days with steam locomotives. And that means like scores of people lost their lives, or, were horribly injured. So we don't want that happening. So to avoid that, we come up with standard time zones. So you know when your train is leaving, you're not going to have two trains on a collision course on the same track. Also, because the telegraph could move messages around the world almost instantaneously, it really makes sense to have a standard 24-hour system of time, right? So the prime meridian is the standard time zone for all clock time, like including our own time zone here at 120 degrees west. Pacific Standard Time is based on, you guessed it, clock time at the prime meridian. All clock time is, right? Halfway around Earth at 180 degrees, we have another important meridian that divides one day from the next. So today is Monday for us in the Western Hemisphere. In parts of the Eastern Hemisphere, on the Eastern Hemisphere side of the international date line, what day is it already? It's already Tuesday. Is it artificial? Absolutely. Would you physically feel any different if you did not know you were crossing the international date line? Of course not. You would not feel any differently. It is artificial, but necessary, I argue, to make our 24-hour system of time zones work. Question.
Well, technically in Europe, right now, like Europe, for example.
Yes.
You guys have the international date line.
Yes.
It's like 10 o'clock at night.
Absolutely. It's many hours later, 8 hours, 9 hours later, depending on where you are in Europe, right, than it is right now. So it's already much later into the night there. It's 3 hours later on the East Coast. Thank you very much. Time and longitude. So what I'm going to do really quickly before we go, we'll do the San Bernardino Mogadishu, and I'll stop, and then we'll pick it up and do more time calculations. There are 24 hours in a day, 24 time zones. 360 degrees, right? Earth rotates 360 degrees every 24 hours on its tilted axis. So how many degrees each hour? If you divide 360 by 24, what do you get? Ooh, ooh, ooh. 360 divided by 24. That means 1 hour of time, one time zone is going to be how many degrees of longitude wide? 15, right on. So we're going to assume every 15 degrees of longitude, we add or subtract an hour of time. Are some time zones wider than 15 degrees? Heck yeah. Are some time zones narrower than 15 degrees? Yes, because we're humans. We make decisions based on political and economic boundaries. Okay. I'm also going to make every meridian of longitude artificially parallel just for the sake of ease to read it. So we're going to look at it like a Mercator type projection, and then I'll stop after this. Okay, so here we go. So check it out. This is going to be amazing and fantastic. And you'll be like, whoa, I'm so glad I stayed like 7 minutes after class for this. No, okay, all right. So, and if you have the answer already, oh my gosh, well, good for you. Okay, so here is the deal. So here's 120 degrees west. We said it's 6 a.m. on Monday. This is question 1, assignment 2. And then we're going to go to our friends in Mogadishu, their time zone, what's called their central meridian. Remember, it's all about east versus west. And we don't know the day and the time. So this is going to be San Bernardino. This is going to be Mogadishu. And in between, we're going to cross the international, sorry, did I say international date line? Just kidding, the prime meridian. So somewhere in between, we're going to cross the prime meridian, right? So, and from our perspective, we are going to go east. So that means we're going to do what with hours? If we go east, we're going to add, right? We're going to go east. So we're going to add hours of clock time. And the question is, how many hours of clock time? So here's my question to you. How much total longitude separates our time zone from their time zone? How much total longitude separates us? So how much do we have from the Western Hemisphere, plus how much do we have from the Eastern Hemisphere? Ooh. Now, I love how you did that because it looks like it. So if you said 75, that would be like 120 minus 45. Now, if both locations were in the same hemisphere, we would totally do that. We would subtract to get the difference. But because both locations are in opposite hemispheres, we're going to do what? We're going to add. So we're going to add 120 degrees of longitude from the west plus another 45 from the east. And what is that total? 165. Love it. So we're going to get 165 degrees of longitude difference. Uh-oh, I'm getting a call here. And how many degrees per hour? 15. Yes, divide it by 15 degrees of longitude per hour. And what do you get? Real quick, 11 hours. So we're going to get 11 hours difference. So that means, because we're east, we're going to add 6 a.m. Monday plus 11 hours is going to equal what time and day for our friends in Mogadishu? 5 p.m. Or if you like military time, 1700 hours, right? But it's going to be 5 p.m. still the same day. It's tempting to say, oh, we got to be Tuesday because they're so far away. But as long as we don't pass through midnight, we're the same day. We're just a lot later. So our answer, 5 p.m. Monday in Mogadishu. So again, east means we add hours. West means we're going to subtract hours. So woohoo, I'm going to go ahead and stop now because I've taken you all way late. So thank you. I'm going to update attendance. We're going to come back and pick up with this. We'll do the structure of the atmosphere, energy interactions. We'll talk more about assignments 3 and 4, and then we'll get into 5 and 6 later in the week as well. So thank you all. I appreciate you, and I'll get this video posted ASAP. So thank you. I appreciate you all. Thank you. Thank you. All right. So hopefully, thank you. I appreciate you all.